All right, so I'll tell you what I told the last section. So I briefly had the high score, but I was soundly knocked out by more than twice the score, so the bar has been set quite high.
Who is that?
I don't know.
Well, that's William.
Okay, yeah.
Row, I think.
So level 19, killed by a griffin. There you go.
I got killed by an ice monster on level 2.
Oh, I hate ice monsters.
Use the bow.
Yeah, use the bow every time.
If you have leather armor, that helps too. But I had a cosmic potion this morning, so I couldn't tell what was what, and there was an ice monster. It's like, I wouldn't have fought you if I knew it was you, dude. So, all right. So I posted a study guide for the midterm, but I'll go over it tomorrow because not everybody is here who would be here tomorrow. But you can look through it. There's no surprises in there really. But glance over that, and if you have specific questions, you can ask those. But I'll kind of talk through it tomorrow. And your final is on Friday, so your midterm is on Friday. So yeah, not your final.
It's your too.
Yeah. Although this is like week 5, so Friday's the halfway point of the course, which is
Hooray.
amazing. Yeah, that's good stuff. So I wanted to talk more about trees, and I want to talk about traversing trees. So when we talk about traversing a data structure, that's a general term. It means somehow going through everything that's stored in the data structure in some particular order. When we traverse a list, we usually start at the first node and we just move from each node to the next node. It's really the only option you have. If we have a hash, we don't really have a predefined way to traverse the data in the hash. There's nothing we can do from outside to say, you know, give me the first thing in the hash if we don't know how the hash is implemented. But we mentioned sometimes there's functions that are provided like get first key, get next key, which would let us traverse. With a tree, there's some very natural ways to traverse the information. And let's just kind of work with an abstract tree. So there's a tree with 7 nodes in it. And there's 3 fundamental ways to traverse this tree, and they're called LNR, NLR, or LRN. And LNR is also called in order. NLR is pre-order. LRN is post-order. Okay, what do these things mean? L is left, R is right, N is the root node. So we're mainly going to talk about LNR, in order traversal. And the definition of traversing a tree is recursive. So LNR, traversal. So let's traverse some tree T. And this is LNR in order. Bless you. Okay, so the first step, if T is null, just return. If the tree is totally empty, if there's no nodes in the tree, there's nothing to traverse. There's no work to do. So if someone says, hey, traverse this tree for me, we just say, okay, we're done. Otherwise, what we're going to do is traverse the entire left subtree of our original tree. So if this is our original tree, we're going to say, okay, well, first I'm going to traverse this B, D, E tree. And then I'm going to print the root, which is A. And then I'm going to traverse the right subtree. So it's a recursive definition. So what does recursion mean? It means you have some friends who can do the same thing that you're trying to do, but you're going to give them a smaller problem to work on, and when they give you back their solution, you're going to use that to come up with your solution. Right? So it's deferring some of the work to a friend. So you're contacted by a client and they say, I'd like you to traverse this tree, please. And you say, sure, no problem, that'll be $100. And they're like, okay, that's fine, that's a bargain. So they give you $100 to traverse this tree. So what do? You say, is the tree null? No. Okay, if it was null, you'd be done. So you have to do three things. You have to traverse this subtree, and you have to print out an A, and you have to traverse that subtree. Okay, so you talk to two friends and you say, hey, can you traverse this tree for me? And they say, yeah, it'd be $10. You're like, okay, give them $10. They traverse this tree and they print out a bunch of stuff in the process. And then you print out an A, and then you take this and you hand it to a friend and say, can you traverse this for me? And they traverse it, print out some stuff. And then everything that was printed, you hand that back to your client and you say, here's your tree traversal. We're done. And you never actually did much work. You printed out the root and you passed along subtrees to a friend, and whatever they said the traversal should produce, you went ahead and printed that. So your friend who you handed this tree to, what do? Same thing. They take this subtree, hand it to a friend, say, traverse this, please. They print out a B, and then they take this, hand it to a friend, and say, traverse this, please. And the friend who was given the D to traverse, what do?
Returns D.
Ultimately, yeah. Technically, from this algorithm, what they would do is they'd say, let's look at the left subtree, that's null. So they'd hand a null tree to a friend and say, can you traverse this for me? And the friend says, yeah, I'm done. Okay, and then they print out the root, which is a D. And then they take the right subtree, which is null, hand that to a friend. Can you traverse this? Yeah, I'm done. Okay. And now they've finished traversing D. So that red friend who was traversing this gets back the traversal of this subtree, which produced a D, and then they print out a B, and then they pass that E to a friend, and that friend will go ahead and print out an E. And the original person who was trying to traverse this entire tree, they just finished this first step, which was they traversed this left subtree and it produced this. And now they're going to print out the root, that's step 2, and then they're going to ask someone to traverse this. And this is going to give you F and C and G. So if we did this on an actual binary search tree, say this, and you do this, first we traverse this subtree, which means print out the left, and then the root node, and then the right. That's the left subtree of the original, print out the root, and then traverse this subtree, which means traverse the left, print the root, traverse the right. Your data comes out in order. Okay, so if it's a binary search tree, left node, right traversal always gives you the data in order, increasing order in this case. Now, if you want to do node left right, this means you print out the root node first and then traverse the left subtree and then traverse the right subtree. All you got to do, move this print statement up here. And if you want post order, just move this print statement below the second traversal. And if you wanted right node left, just swap the left and right parts. Do the right subtree, print the root node, do the left subtree. Right node left, you'll get your numbers in decreasing order. And this is, or will be, a very natural way to think about traversal. He's in this recursive sense. But what's going on can be really confusing to think about. But let's take a look at it anyway. So someone says traverse, and this is the argument to the traverse function. It's a tree, which say looks like this. So you're calling this traverse function with an argument like that. And here's the 3 steps that are going to be done by this traverse function. The first step will be to traverse this subtree. The second step will be to print the root node. And the third step will be to traverse this subtree. Okay, that's all that the traverse function is going to do. 3 things. It just so happens the first and third things are calls to another function. So what's going to happen when you call traverse with this tree? First thing it's going to do is traverse a tree consisting of a single node 10, and then it's going to print the root, and then it's going to traverse a tree consisting of a single node 30. And same thing when you traverse 60, 50, 70. It'll traverse 50, print 60, and traverse 70. And when you say traverse this tree, it's going to traverse the left subtree, which is null. It's going to print the root, and it's going to traverse the right subtree, which is null. And same thing here, and you get the idea. Same thing down here. And when you call traverse null, it's just going to return. Right, that's step 0 of our traverse function. If the tree is null, just return. So now we can actually trace what happens when we say traverse this entire tree. First we say traverse this, which says traverse 10, which says traverse null, and then says print out a 10, and then says traverse null. And we come back to here, and we print a 20, and then we come to here, which says traverse a null, print a 30, traverse a null, we come back to here, that's the end of that function, so we return back here, we finish this, now we print a 40, and now we do this, which says traverse a 50, and so on.
It's like a tree of traversal.
It's exactly like a tree of traversal. In fact, if you were to map out this tree, it would end up looking like the tree that you were originally traversing. If it wasn't symmetric, it would have the same shape in some sense. So if we try to do this by hand, we need to write all of this stuff out. And basically what we're doing is the same thing when we're running a maze. We start off at the 40, we say, okay, first I have to go to the left. So we have to put a finger here and say, I got to come back here eventually and print the 40 and then do the right. Well, we come down here to the 20 and we say, okay, I got to traverse this. Okay, I'm going to go to the left first, but I'm going to come back to the 20 eventually. We go on to the left, we print out the 10. And then we say, where was I? Oh, yeah, my thumb. Okay, print out the 20. I got to go to the right. Okay, we do the right part. And then when we're done with that, we say, okay, where was I before I got to the 20? Oh yeah, my finger's up here, so I'll print the 40. And now I'm going to come down to the 60, right? And we got to keep track of where we are at each of these points. But when we go back to a place we were previously, we're always going back to the last place that we had to make a decision. Right? We might come down, 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 and get to a point where we have to go both left and right. When we're done going left and right, we're going to come back to that and go to the previous place we were at. That's inherently a stack-based structure. The last place that we made a decision is the first place we're going to go back to. And this works because when you make function calls on a computer, you're storing information on a stack. You're storing the return address on the stack. You're also storing local variables on the stack. And all the variables that you define inside a function, when you make a call, those are tucked away safely. And when you come back from a call, they're returned back into being whatever value they were before the function call. So that's inherently stack-based. But we don't need to worry about that once we are comfortable with doing things like this, calling traverse inside traverse. And this will blow up if we don't have this step 0. Because if t is null at some point, when we try to traverse the left subtree of something that's null, that's a seg fault. Because null isn't pointing to a node that has a left subtree. It's going to say you can't access memory location null, and will seg fault. So we need this base case here to kick us out of the recursion. And this is another form of mathematical induction. Right, there's a base case, there's some inductive steps where we're using the fact that this works on a smaller tree to make it work on a larger tree. Because we know the left and right subtrees are shorter than the original tree. They have less stuff in them because they don't include the root or anything on the right. And so each time we call this, we're passing it a tree which has less stuff in it. But if the tree gets so small that it has no stuff in it, we're not going to do any more recursion. We're just going to return at that point. That's basically our base case. But you could prove this works with a formal proof using mathematical induction. We don't have to do that, though. You can trust me. All right, let's look at another example. You don't have to copy this, I'm just having fun. I'm probably not going to use most of these. But my trees are normally so boring. They almost always look like this. So, you came in through the snow, you deserve a better tree. So, here's a hopefully valid binary search tree, if I didn't make any mistakes. How do we know it's a binary search tree? Everything on the left of a node should be smaller than the node, and everything on the right should be bigger. And I think I've adhered to that correctly. So let's talk about searching. Suppose we want to search for the number 31. And all we have is something that tells us where the root of the tree is. Well, since we know it's a binary search tree, we can do the following. First of all, if the root's equal to 31, we're done. We can say, yeah, we found your node, it's in the tree. That's easy. Okay. If the root is not equal to 31, we can do our old high-low trick. Is 31 bigger or smaller than the root? If 31 was smaller than the root, we never have to check anything to the right, because everything to the right is bigger. So we could say, well, let's just search this subtree. If 31 was bigger than 40, we'd never have to check anything to the left, because anything bigger than 40 has got to be in this right subtree. Okay, 31 is smaller than the root, so we basically say we don't care about any of this stuff. If 31's in our tree, it's somewhere in this subtree. So we can move down to this node and say, well, is this 31? No. Is 31 smaller than this? No, 31's bigger, which means now we don't have to worry about any of this stuff. because if 31 is in our tree, it's got to be in this subtree. Well, the root's not 31, but 31's bigger, so we can ignore all of this. And let's search here. It's not 31, but 31 is smaller than that, so we can ignore this. Let's just search this subtree. And now when we say, hey, let's check the root, hey, it's 31. We found our 31. If we were searching for the number 33, same process, smaller than 40, bigger than 20, bigger than 30, we'd come down to this tree. 33 is bigger than 32, so we would search this tree. 33 is smaller than 35, so we would try to search a null tree on the left. And as soon as the tree we're searching doesn't have any nodes, we can immediately say 33 is not in that tree. Nothing's in that tree. And we'd say, nope, node's not found. So we could write an algorithm for this. So we're searching a tree T for a number n. So if T is null, we can say n is not found in the tree. If the root's equal to n, we can say it is found. If the number we're looking for is smaller than the root, set T equal to the left child and go back to step 1. Otherwise, n must be bigger than the root. Set T equal to the right child and go back to step 1. And so there's a 4-step iterative algorithm. There's no recursion in here. I don't call the search function inside here. I just have some go-tos or a loop. See if the tree is null. If it is, it's not found. See if the root matches n. If it is, it's found. If our number is smaller than the root, change our local variable t to point to the root of the left subtree and come back up to step 1. Otherwise, set tree to the root of the right subtree and go back to step 1. And that's exactly what we were doing here. 31 is smaller than that, it's bigger than that, it's bigger than that, it's smaller than that. And eventually we get down to here, and step 2 will fire and say, yep, that's equal to the root, it's found. So this is iterative. So no recursion in there. And it's a nice iterative solution in this case because at each point we're making a single decision. Should we move to the left or to the right? And we never have to go back and make a different decision. If we're looking for the number 55, we start here, we move to the right, we move to the left, we move to the right, and we hit null, it's not found. We don't have to come back here and search to the right, for example. Right? So this works well with just a straight loop. But we could also code this recursively. So how would you recursively search this? If you had a friend who was able to search trees for you, how could you utilize them to minimize the amount of work you have to do to search a tree for a number.
Get some more friends to search a branch of the tree.
Okay. How many friends you need?
How many branches are there?
Well, if you're at the root, you only got 2 branches coming off the root. And I'm kind of a thoughtless friend. I don't really care how much work my friend has to do. So I'm just going to take my original tree. I'm searching for 31. I'm going to say, is 31 equal to the root? No. Is there stuff in the tree? Yeah, so I got to do some work. 31 is smaller than this, so I'm just going to take this whole left subtree. I'm going to give that to a friend and say, can you tell me if 31 is in this tree? And if they say yes, then I'm going to say yes. If they say no, then I'm going to say no. And if I'm searching for 55, I would take this subtree and give it to my friend and say, can you tell me if 55 is in this tree? And whatever their answer is, that's my answer. And if I'm searching for 40, I'm going to look at the root and say, yes, 40 is in this tree. I'm not going to have to bother my friends. And if someone gives me a tree that has nothing in it and says, does this contain the number 5007, I'm going to immediately say no, because there's nothing in the tree. So my job is really, really easy. So if t is null, return not found. If the root data matches our number n, I'll just say it's found, and I'm a hero because I got the answer. If the number I'm looking for is smaller than the root, what am I going to return? I'm going to return whatever I get when I call search on the left subtree, looking for the number n. Otherwise, I know that n is bigger than the root data, and so I'm just going to return search t.right, comma n. So there's a recursive version. And there's no looping. I don't need a while loop. I don't need an exit condition on my while loop. I don't need a temporary variable. Right? I have 3 things I'm going to do. Either say it's not found because there's nothing in the tree, that's easy. Or say it's found because it's equal to the root, which is just one if statement. Or I'm going to call search. And whatever search returns, I'm going to return that. So search we can do recursively like this. We can do it iteratively with a loop, where we're moving down and continuing to check. The behavior in the end is basically the same. All right, so we'll code some of this up in a few days. But I mean, this is pseudocode, but it's basically your search algorithm, right? You have to use arrows instead of dots and 2 equal signs for equality and uppercase null, but I mean, it's basically C code. And it's really 4 lines of C. And the recursive part, of course, is that, we're using the function search inside the function search. But again, we can prove that works using mathematical induction. We could make a proposition that the search function works for a tree of a given height. And when we take a left or a right subtree, the height of that tree is going to be smaller than the original tree because we don't have the root anymore. And you can show that this works for a tree of height 0 or -1, and then you can do your induction. So this was our iterative version of search. And it looks a lot like the recursive version, right? Instead of going back to step one, we just make a call to search. Traversal is a different story. So traversal, our algorithm for, again, left node right, was if the tree is null, nothing to do. Otherwise, traverse the left subtree, print the root data, traverse the right subtree. So let's look at traversal. With an iterative solution. And this is weird, and I'm going to use a lot of pseudocode here, and I don't want to get caught up in the details of the pseudocode, but let me put down an algorithm, and then we can go through it with a sample tree and see if it works. So 5-step algorithm for traversing a tree in order. Step 1, push the root. So we're going to use a stack. So push the root node onto the stack. Step 2, if t left is not null, push it and go to step 2. Step 3, pop whatever's at the top of the stack, call that t, print out the data at the root of t, and that's all we do. But if stack was empty, then you're done. Okay, step 4, if t right is not null, then push it and go back to step 2. Step 5, go back to step 3. So this is fairly bizarre, and I don't want to get too tripped up on details, but let's play with this. So here's a slightly peculiar looking tree, and let's make a stack, and we'll grow the stack from top to bottom, so top of stack will be at the bottom. And let's make an output section and record what we print when we run this algorithm. So step 1, we push the root of t, so the root of t is 40, so that gets pushed on the stack. Step 2, see if there's something to the left of t, and there is, it's not null. So we're going to push that node onto the stack, and we're going to go back to step 2. So now we're going to see if that 20 has something to the left, and it does. So we're going to push that 10 onto the stack and go back to step 2. So my pen is pointing at the current node t. Okay, see if t has something to the left. No, it doesn't. So we go on to step 3. Step 3 says pop top of the stack. So pop off the 10 and print it. And that's our new node t. And then step 4 says if there's something to the right, which there is, push that onto the stack. So we push a 12 and go back to step 2. Okay, so if there's something to the left of here, we would push it. There's nothing to the left of 12. So next step says pop the top of the stack and print it. So there's a 12. And then if there's something to the right, push that. Well, there's nothing to the right of 12, so we go back to step 3, and step 3 says pop the top of the stack. So top of the stack is a 20, so we pop that and we print it. And now we say, is there something to the right of 20? Yes, there is, so we push what's on the right, and we go back to step 2. There's nothing to the left of 30, so we pop off the top of the stack, we print it. And if there's something to the right of 30, we would push it, but there's nothing, so we go back to step 3, which says pop again. Well, the only thing on the stack now is a 40, so we pop off the 40, we print it, and now we say, is there anything to the right? Yes, there is. There's a 60, so we're going to push the 60, go back to step 2. If there's something to the left, push it, no, so pop the top of the stack, there's our 60. And then if there's something to the right, push it. There's a 70 to the right, so we push a 70 onto the stack. Go back to step 2. Nothing to the left. Pop the top of the stack is a 70. Print that. Nothing to the right to push, so we go back to step 3, which says pop the stack. There's nothing left in the stack. We're done. And there's your output, and it's the in-order traversal of the tree. And this is achieving the same thing as this. The difference is when we make these recursive calls, the system is using the stack to preserve the current value of t, the argument that was passed to traverse. That's what we're mimicking here. So the output's going to be the same, but this to me is fairly random looking. Right? Whereas this to me is basically the definition of traversal. How do we do in-order traversal? Traverse the left, print the root, traverse the right. That's the definition. So in some cases we can do an iterative solution and it'll make perfect sense, but in some cases it's not. And the reason that traversal is so much more complicated is because every time we come to a node, we've got to remember where we are, do some stuff over here, and then do some stuff on the other side. And we need to keep track of all these places we're putting our fingers down, just like running a maze. You need to know where to go back to the last decision that you made. So we've got all of this stack structure in here. But more and more we want to think about recursive solutions. And the more you work with these, the more comfortable they become, and eventually you can't imagine doing this stuff anything other than with recursion. Okay, that's the place we want to move into. And so traversing a tree in these different styles takes practice. So if we wanted to do left-right node traversal on this tree, we would say let's go all the way to the left and then the right and then print out the root node. So that's going to print a 10 first. In traversing this, we'll print the 10 and then the 30 and then the root node. And then we're going to do an LRN traversal on this, which will be a 50, a 70, and a 60. And then, having done the left and right subtrees, we'll do the root node of the original tree, which is 40. And that's weird. That's not like in sorted order. It's just kind of a different traversal order. But post-order LRN traversal is useful sometimes. And here's an example. So we talked about RPN. Where we were trying to evaluate an arithmetic expression. We can take this expression and we can turn it into a tree. And basically, if we have a pair of operands and an operator, we're going to make a little tree out of it. So A, B, with a plus at the root, this means take A and add B. C plus D we can write as this. There's C and D, and the operation we're performing on them is a plus. And our original expression is this expression, that expression, multiplied together. So we can pretty easily transform an algebraic expression into a corresponding tree. Well, guess what happens if we traverse this tree in post order? We come all the way down to the, well, we're going to traverse this tree first. We're going to come down to the left, and then down to the right, and then print the root. And then we're going to traverse this tree, which will be left and right and root. And then, having traversed the left and the right of the original tree, we print out the root of the original tree. That's our postfix representation of that algebraic expression. So to convert from an algebraic expression to an RPN expression is fairly straightforward. Take your original expression, build an expression tree, and then traverse it in left-right node, reverse Polish notation. Traverse it in postfix order, and you get the postfix expression. So these things pop up in all kinds of weird ways. All right, so we're going to stay abstract for a while. Well, let's just take a look at a little bit of C code. So what does a node of our tree look like? Well, if it's storing integers, we'll say integer data. And then a struct node pointer called left. Another struct node pointer called right. And that's really all we need for a node. Piece of data and two pointers, one pointer to the left, one pointer to the right. And those pointers might be null, meaning there's nothing to the left or right, or they might be the address of another node. And it's just slightly more complex than the linked list. All right, we have one extra field in there, and so each node points to potentially two things. But coding it up, the mechanics of that is the same as what you've been doing with linked lists. Arrows and stars and all that stuff. So let me give you one more thing to keep in mind, and we'll come to this in probably another week. So our favorite boring tree, right? That's a binary search tree. To do a search on this is a very efficient operation, right? If I'm searching for the number 30, it's going to take me 1, 2, 3 operations. Compare it to a 40, compare it to a 20, compare it to a 30. If I'm searching for the number 33, it's going to take me 3 operations compared to a 40, 20, 30, and at that point I know it's not found. If I'm searching for a 40, that's going to be really quick because it's right there at the root. But if this tree had twice as many things in it, worst case, it's going to take me 1, 2, 3, 4 operations. Every time I double the number of nodes in here, the number of steps I have to do a search goes up by 1. Double the amount of data, you take 1 more operation. Okay, this is high-low. If you can guess a number from 1 to 100 in 7 guesses, you can guess a number from 1 to 1,000 in 10 guesses. And from 1 to 2,000 in 11 guesses, and 1 to 4,000 in 12 guesses. Right, so 1 to 1,000,000, 20 guesses. It's a very slow growth rate. It's basically order of log n. Because the number of steps you have to do to search is a function of the height of this tree. Remember, height is how many hops it takes to get from the root to any node. That's the number of steps that you have to do. Because at each point in your loop or in your recursive call, you basically move down 1 level in this tree. And if the longest number of steps from the root to any node is n, after n steps, you'll be at a leaf node. And that's either your number or its children are null, and you can say the number is not found. Right, so is that a binary search tree? Take a vote. How many say yes? How many say no? How many don't want to participate? Binary search tree, you can have at most 2 children. Every child on the right's bigger than the root. Every child on the left is smaller. This satisfies those definitions. But it's a really poor looking tree, right? You'd want to hire a new landscaper. Because this is really just a linked list, right? And if we're searching for the number 70, we have to do 1, 2, 3, 4, 5, 6, 7 comparisons. If you're searching for a number that's not in here, you're going to have to do 7 comparisons to conclude that. Whereas here, you're going to have to do 3 comparisons. So this is a tree, that's a tree, but they're not equal in some sense in terms of performance. This is going to have log n performance. This is going to have order n performance.
So is a tree essentially a doubly linked list?
Well, not in the classic sense, but because in a doubly linked list, each node points to the node after it and before it. Whereas here, it's kind of pointing to 2 nodes that come after it. And these don't point back. So it's got 2 links, but they're not constructed in the same way as a doubly linked list. But yeah, it could be exactly the same structure. In fact, your structure would look exactly the same. But you'd probably call it forward and backward.
So is there a way to balance this other tree?
He said it, not me. Yes. So this is called a balanced tree, and this is an unbalanced tree. And in probably a couple of weeks, we'll talk about how to balance trees. And you may get an assignment on that. I haven't decided yet. I've never given that assignment. But there's a number of algorithms you can use to try to make a tree balanced, primarily so that you keep this really good performance behavior of being log n to search and to delete. So we'll talk about that later, and there's a whole, you could spend half a semester long course talking about balanced trees. It's a beautiful area though. So we won't worry about this for now, all right? So tomorrow we'll go over that study guide for the midterm. We'll talk about how to insert into trees. We'll talk about deletion, and we'll play around with some other concepts. All right, stay safe. I'll see you tomorrow.